So now for this third example, I would encourage you to give it a try. Okay, so you've seen it now. We've got a function t that goes from R3 to R3. So as an input vector, it accepts a three-dimensional vector with 3 coordinates. And as an output vector, it gives back a three-dimensional vector with 3 coordinates. And this example says to show that it's a linear transformation. So the process is going to be pretty much the same as the previous two examples. Of course, you've got a different function, so some of the details will work out differently. But for the most part, it's going to follow the exact same flow. So rather than just continuing to watch, because I'm going to work through it now in this video, but rather than just continuing to watch at this point, I would encourage you to pause it, try it on your own, and if you get stuck, then come watch the video. And if you don't get stuck and you do get through it just fine, even better. But maybe still just skim through the work that I do now afterwards to make sure that you are on the right track. So with that said, I'm going to start now. But I would encourage you to try this one on your own before you watch me do it. Okay, so we've got our function t, and we want to show it's a linear transformation, so we're going to verify the two properties. So first of all, we want to show that for any two vectors x and y in R3, t of x plus y is equal to t of x plus t of y. So we're going to start by choosing arbitrary vectors x and y in R3. So they're each going to have 3 coordinates because the domain of this function t is R3. So it accepts three-dimensional vectors as input. So let's say x1, x2, x3 is the first vector, and the second vector is y, which will be written as y1, y2, and y3. So those are arbitrary vectors in R3. All right, well, let's work out t of x plus y and try to show that it's equal to t of x plus t of y. So let's start with t of x plus y. So t of x plus y, well, x plus y is going to be the sum of this vector and this vector. So this is going to be equal to t of, well, the first coordinate is going to be x1 plus y1, the sum of the two first coordinates of each of the vectors x and y. Then the second coordinate is going to be x2 plus y2, and then the third coordinate is going to be x3 plus y3. So now, what does t do to a three-dimensional vector? Well, it seems, based on this definition, it looks like it leaves the first two coordinates unchanged, right? The first coordinate of the input vector is the same as the first coordinate of the output vector. The second coordinate of the input vector is the same as the second coordinate of the output vector. But then the third coordinate of the output vector is actually the sum of all 3 coordinates. So with that in mind, let's apply that here. So the sum of all 3 coordinates is going to be the sum of all 3 of these coordinates. So actually, our third coordinate is going to be quite wide. So I'm going to actually leave myself quite a bit of space here. So the first coordinate and the second coordinate won't change though. So the first one, I'm going to write x1 plus y1. Then for the second coordinate, I'm going to write x2 plus y2. But then for the third coordinate, we're going to add up all 3 of these. So first one, x1 plus y1. Then the second one is x2 plus y2. And then the third one is x3 plus y3. Okay, so that is t of x plus y. We've first added the vectors x and y to get this vector, then this t got applied to it to give us this. Now, remember what our goal is. We want to end up turning this into t of x plus t of y, so we're going to probably split this up into the sum of 2 vectors somehow. So let's follow the same approach as what we did before. Let's break it up into the sum of 2 vectors, one of which has all of the x components, and the other one has all of the y components. So this is what we'll get. The first vector, well, we're going to have x1, x2, and then the third coordinate, let's pick off the x1, x2, and x3. We've got x1 plus x2 plus x3. So Currently, that expression is not equal to this expression, or this vector is not equal to this vector yet, because this one has a whole bunch of y terms that this one doesn't, but we can add those on separately. So our second vector, well, what's going to be left? The y1 and the y2 are missing here, over here, right? They don't show up. So the first term is missing the y1, so we'll just put y1. The second term, here x2 plus y2. Over here we're missing the y2, so we'll have y2 there. And then the three terms that we didn't include down here is the y1, the y2, and the y3. Let's put those down here. So we get y1 plus y2 plus y3. Okay, and that is, well, look, guess what this is, right? This is exactly this vector here. So it's going to be t of x1, x2, x3. That's what this first vector is. And then this vector is actually exactly what you would get if you worked out t of y1, y2, and y3. If you plug this vector into t, you'd get exactly this. So actually what we have here is plus t of y1, y2, and y3. So great, that's done, because this is t of x, and this is t of y. So that completes the first condition. And just in keeping with the tradition here, I'm going to just put a bracket to indicate this is all for checking the first condition. So let's check the third condition now. So we'll take a vector in R3. We only need one vector this time. Remember, one vector and one scalar. So the vector x will be written like that as a general vector in R3. And then we'll write k as our scalar. Okay, so good. Now we want to show that t of k times x is equal to k times t of x. So we're going to start in the same way we started the previous ones. We're going to start by computing t of k times x. So again, the brackets around the kx, that indicates that this multiplication happens, and then the function t gets applied to the result. So what we have here is t of, well, whatever you get if you multiply the vector x by the scalar k. So this k is going to get multiplied onto all three of those coordinates, and we'll have kx1, kx2, and kx3. So that's what we get. Well, now we're going to apply the definition of t, right? T will use this rule. So the first two coordinates, the first two coordinates are going to be unchanged. So we're going to have k1, pardon me, not k1. I'll just put it over to the right. We're going to have k times x1. That's what I meant to say, because the first coordinate gets copied over directly, just like here, right? In the definition of t, the first coordinate x1 just gets copied over directly. The second coordinate x2 gets copied over directly. So we'll have k x2. And then for the third coordinate of the output vector, we get the sum of all three coordinates of the input vector. So we're going to have all three of these added together for our third coordinate. So we'll have kx1 plus kx2 plus kx3. Okay, so that is the image of the vector kx under the function t. Right? This is what you get. This is t of kx, completely worked out now. So what we should probably do now is try to get that k out of there, if at all possible. And the first step would be to notice your third coordinate has all these three terms have a common factor of k. Let's factor that out. So we'll have k x1, kx2, and then k times x1 plus x2 plus x3. And then now, all three of the coordinates, the first, second, and third coordinate, all have a common factor of k. So we can pull that k out, which is good, because that's usually going to be your goal for problems like this. Because remember, we want to show that this is equal to k times t of x. So automatically our goal is to try to get that k out of there. And it turns out it's going to work out really nicely, because once the k factored out of all of these three terms, we now have the third coordinate has k as one of its factors, just like the first two coordinates. So let's pull that k out. and we'll end up with x1, x2, and then x1 plus x2 plus x3. And now this worked out great because this is exactly t of x1, x2, x3. So we're almost done. This is k times t of x1, x2, x3. And then finally we're done on our next step because t of x1, x2, x3 is t of x. So that's exactly what we wanted, right? We want to show that t of k times x is equal to k times t of x. So that's how we finished verifying the second condition. Okay, so great, that means we're done. Therefore, t is a linear transformation. And that completes that example. All right, so I mentioned before this section started that, well, and the section is even called matrix transformations. So up until this point, matrices haven't really played a role. But now that's going to change. We're going to look at the connection between matrix multiplication and linear transformations, and which starts with the following. So let's go through this. Let A be an m by n matrix, so it doesn't need to be square, it can have absolutely any dimensions. And we'll define the function capital T, and then the A is a subscript, just to indicate that this function we're defining is associated with this matrix A, and it comes from this matrix A. But that's just a label for the function. T with the subscript of A, that is just the name of the function we're defining. And it looks like it goes from Rn to Rm, so it takes as input an n-dimensional vector and gives back as output an m-dimensional vector. And so what is the definition? Ta of x is defined to be the product of A with x. Well, and you have to really be careful how you represent the vector x for this to make sense. And that's what the rest of the sentence is for. It says where x in Rn, so the n-dimensional vector x, is identified as an n by 1 column matrix. I mean, in fact, maybe this isn't the... If I were to reword this, I would say is represented as an n by 1 column matrix. Or really just say that the vector x is written in column form. The purpose of that is if we write x in column form, then it's going to be an n by 1 matrix. And if A is an m by n matrix, then we have the product of an m by n matrix and an n by 1 matrix, the result of which is going to be an m by 1 matrix, which is a column vector in Rm, which is why this truly is a valid header for the function that's defined in this way. So this is called the matrix transformation associated with this matrix. Okay, and we'll certainly talk more about that, but for now, is this a linear transformation or is it just a function? Like, we've looked at 3 examples now of functions and we've shown that each of them are linear transformations, and it's no joke to do that. It's a fair amount of work and details to grind through in order to verify that these, well, this one, for example, to verify that this was a linear transformation. I mean, there was no shortage of work done on this page in order to get there. So a natural question would be, is this going to be a linear transformation? And the answer actually is yes. And even though we don't even know what the matrix A is, I don't even have to tell you what the matrix A is, and I can already tell you that this is going to be a linear transformation, which I think that's a pretty neat fact. And what may be even more surprising is that it's easier to prove than this problem was to solve, even though we had so much specific information in this case. So let me run through that. So first, let's make the claim. So claim Ta, so T with the subscript A, this is the name of the function here that's defined in this manner. Ta is a linear transformation. So what is the first step? Well, we need to show that for any vectors x and y in Rn, Ta of x plus y is equal to Ta of x plus Ta of y. So let's start with vectors x and y in Rn. And we will assume that they are represented by column matrices, just like this vector x is in this definition, right? The whole point of this definition is it depends on the fact that x is written as a column matrix. So I'm not going to actually write out the coordinates of these vectors because it actually just turns out to not be all that useful to do so, and it just makes a whole lot more work than we need or want. So it turns out that this is enough. So let's actually apply TA to x plus y and see if we get TA of x plus TA of y. Well, TA of x plus y, by definition, what does TA do to an input vector? It multiplies on the left by the matrix A. So what we're going to get here is A times x plus y. Now here's where we're going to take advantage of properties of matrix arithmetic. This is matrix arithmetic, right? X is a column vector, so it's written as a column matrix, and so was y. So we got these two matrices added together and then multiplied by A afterwards. But matrix multiplication distributes into matrix addition. We saw that in section 1.4. So that is a really nice convenient factor. We can distribute the A into the brackets. So we're going to get A times the vector x. Remember x is a column vector, and so is y. So this is A times y. And that actually, A times x, that's actually the definition of TA of x. And then A times y, that's the definition of TA of y. So that completes the first check that we have to do, because that shows that TA of x plus y is equal to TA of x plus TA of y. It was even less work than most of our examples were, even though we didn't even know what the matrix A was. So sometimes the abstract case is even simpler than the concrete case. Not always, but sometimes it is. Okay, so that is, if I'm keeping with the tradition, this is to check property 1. Then to check property 2, we're going to need a vector and a scalar. So let's say x is an Rn, and k is just some real number. Let's work out TA of kx. All right, and we want to show that that's equal to k times TA of x. All right, well, what does TA do to this input vector kx? Well, what does it do to any of its input vectors? It multiplies it on the left by A. So this is going to give us A times kx, and now we've got, remember the vector is a matrix here, so we've got a matrix multiplied by a scalar product of a scalar times a matrix. So this scalar can be pulled right out. That's another matrix property in section 1.4. If you have a matrix multiplied by another matrix, which is the product of a scalar and a matrix, that scalar can either be multiplied onto this factor, or we can pull it over, multiplied onto the A first, or we can completely pull it out of the product, which I'm going to do now, and just multiply it on after we multiply the A and the X, right? The key here is that K is a scalar, right? If all three of these were matrices, you would not be able to pull the K out in front. But because K is a scalar, we are allowed to do that. And then now we're done on the next step, because AX, that's exactly TA of x. So this is equal to K times TA of x. And that's what we wanted to show. That verifies the second condition. TA of kx is equal to K times TA of x. So that completes the proof of the second condition. So there you have it. So that we can say, therefore, TA of x is a linear transformation. Okay, and I'm just going to draw a proof box here because that completes the proof that we were working through here in general.